Hi, my name is Chelsea Chandler, and I'm presenting work on integrating computational safeguards into AI-mediated clinical decision support systems. This work was done in collaboration with Peter Foltz, Alex Cohen, Terje Holmlund, and Brita Elvevåg. At CLSIG 2019, we presented work on automating the scoring of a story recall task with NLP and AI methods. I'm going to sum that work up briefly before getting into the current project. So participants with serious mental illness and healthy controls listen to a short story, and then we're asked to retell it both immediately and after a delay of 30 minutes in as much detail as possible, which follows a similar format to the traditional Wechsler memory test. We had human raters rate these recalls on a scale of 1 to 6 and created a ridge regression model to automate this rating. The model was based on the number of unique words or types spoken in the recall, the number of common types between the original story and the recall, and the BERT score between the original story and the recall. The BERT score is a similarity metric that was created to produce a score of how close a machine-generated translation is to the gold standard of some piece of text. Specifically, it creates a matrix of BERT cosine distances between words in one text to words in another. Alignment between the words in both texts is produced greedily with the maximum cosine distance for each word in one text to another in the reference. All distances are averaged and inverse document frequency ratings are optionally incorporated. There's a link at the bottom right of the poster down here to our CLSIG 2019 paper with more details of the task and the automation of that task. Now, after successfully automating a whole slew of neuropsychological tasks, our team started discussing why most of these approaches haven't been integrated into real clinical practice. With such high stakes in real practice, we concluded that these models must have safeguards placed on them to avoid spurious predictions, and that researchers must investigate where in feature space they tend to be unstable or bound to not generalize to new populations. So for this project, we explored outlier detection and further investigated the extent to which our model showed inductive bias. So with our story recall data and our regression model in hand, we first applied an isolation forest algorithm to the full data to detect strange data points. The isolation forest discovers minority data points that have attribute values that differ from those of the usual instances. So specifically, the algorithm isolates examples by selecting an attribute at random and then selecting a random split value between the maximum and minimum values of the selected feature. Anomalous examples will have shorter paths from the root to the leaves in their isolation trees than the normal examples, since they need fewer partitions to be isolated. This algorithm is well suited for high dimensional data sets and has proven to be an effective way of detecting outliers and anomalies. Furthermore, it works especially well for behavioral data, as normal regions tend to be more variable than in other domains. The algorithm detected 18 data points that were either invalid or erroneous, and there is a contamination threshold in this algorithm that can be tuned to catch more or less outliers, depending on their approximate distribution in the data set. The plot in the middle panel here shows the story recall data, where each peak is associated with a recall rating from 1 to 6, and the scatter plot below is the actual data that makes up the peaks. The 18 outliers are shown with a cross. We can see that many of these outliers have colors that do not line up well with the peak that they fall under, which clearly indicate a class outlier. A similar plot is shown on the right panel over here, with the relationship of two features being displayed. The number of common types is on the x-axis and the BERT score is on the y-axis, which are two features that should, for the most part, agree. And outliers are again shown with a cross symbol. One of these examples, the topmost red one, had a very high BERT score, even though only a couple words were spoken, which illuminated an error in that attribute. So outliers are important to detect both in the research stage in order to update or exclude certain examples from affecting the model in a negative manner, and in the clinical setting so that spurious decisions are not made on abnormal data, and these data points can be passed on for humans to review, creating a human-in-the-loop machine learning system. Next, to investigate generalizability of the model, we used stratified sampling to generate smaller subsets of the data for training and testing our model. And we found that even with only 25% of the data, as shown in this table in the right panel, there was not a significant decrease in the model accuracy, which was great. We also did a transfer test from the current studies population to another population of people with affective disorders, in contrast to the initial population of seriously mental ill participants. And we found that the correlation from training on one population and testing on another was 0.84 or 0.86, depending on the direction of that training testing allocation. And we can see that with the full data set trained and tested on our initial population, we have a 0.91 correlation. We concluded that finding representative data is extremely important in machine learning. In some cases, such as the story recall regression model, it may be best to get as much data from as many people as possible. In other cases, especially when dealing with extreme diversity between individuals or subsets of individuals, it may be best to only use data that behaves in a similar fashion to the example currently being tested, or even collecting many samples of data from the same person and only generating predictions from that person's own data. In experiments involving NLP methods, it is common to deal with high dimensionality from features like word embeddings, parser outputs, and so on, which make interpretation and understanding of models really difficult. So features often go beyond normal distributions, and as such, there tends to be high variability in data distributions. Thus, it's really important to create models, methods, and tools that allow us to better understand the feature space and determine whether attributes or classes may violate assumptions. We advocate that approaches such as these be incorporated into machine learning and NLP-based clinical research and implementation. With the complexities inherent to models based on many features, high numbers of parameters, highly variable human behavioral data, and extremely high and potentially fatal stakes for mistakes, it is critical to establish methods beyond model designer intuition and assuring robustness and that predictions cannot be made on out-of-range data or data that lies in areas of instability. Thank you for listening to my presentation of our work. If any questions do come up, please feel free to reach out to myself. My email is chelsea.chandler@colorado.edu. Thanks.